My name is Ellen Bitstam, and this is my final exam for my Organic Chemistry 1 course. What this question is asking us to do is to add the curved arrows to show how the first Renaissance structure can be converted into the second in the reverse. So what we want to look at is the first and the second. We see that this lone pair has moved down and became a double bond over here. And we see that this double bond here has been broken and it is now a lone pair on this carbon. So in order to make one look like the other, we need to bring this lone pair down, and it is now bonded between the carbon and carbon, making it the second Renaissance structure. And then we need to bring this double bond here, it's broken, and is brought over to this carbon here, giving us the second Renaissance structure with the lone pair right here. Now, in order to make it reverse and go back to the first, we need to add this lone pair here and break this second double bond, here, and put it back onto the carbon. Question 2, we're supposed to draw the products of the proton transfer reaction. We need to label the acid and base in the starting materials and the conjugate acid and the conjugate base in the products. We're supposed to show how the arrow formalism between the base reacts with the acid. So what I went through here, and I wrote down the acid base and the conjugate acid and conjugate base. In order to know that it's an acid, it has to contain many hydrogen atoms. Also, the alcohol group kind of gives it away a little bit. And then as well as, this is carboxylic acid from the functional groups. Also, this lone pair, the oxygen has more lone pairs on it than this oxygen does. So this means that this is the base. So what happens is that this oxygen will come over and it will grab the hydrogen. The hydrogen is then cleaved and the lone pairs go over to this oxygen here, creating our conjugate base and our conjugate acid. We're supposed to circle and name the functional groups in each molecule of penicillin G, which is an antibiotic. What I went through, and I went ahead and I labeled them, but I was going to show you which one I meant. So the first functional group, and these are just something that you have to know. This is a benzene ring right here. Right here we have an amide, as well as an amide right here. We also have a carboxylic acid right here, and we have a thioether right here. So this is our 1, 2, 3, 4, and 5. However, 2 and 3 are the same type of functional group, so both amides. With this, we're supposed to indicate the chiral centers, with an asterisk. One thing before you can do that, you need to understand what a chiral center is. Or how to identify one rather. There's a tetrahedral shape. There are 4 different things attached to the middle. So, and even lone pairs can count. One thing to keep in mind that double bonds are as if, like right here, where we have a carbon double bond to an O, you have to think of it as a carbon bonded to an O and bonded to an O. So there's 2 oxygens here instead of 1. We have to remember that, and then we also cannot have multiple lone pairs. So bromine has 3 lone pairs. Those are 3 lone pairs. They're not different. So that is not a chiral center. However, if we go around starting with this benzene ring and kind of go around into a circle, we can see by what we know we need to have 4 different things, and that lone pairs can count. We can then go and look on what is attached to our center atom. So this nitrogen, 1, 2, 3, with a lone pair, so that is 1. Bromine cannot. This carbon is not 1. So we just have to keep going to make sure something's different. This nitrogen has 4 different bonded. Keep going. This carbon has 4 different bonds. This nitrogen has 4 different bonds. No, this doesn't because it has that double bond. This carbon right here has a different 4 different things attached. This one does not. It has 2 hydrogens. This one does not. This one does. This one also does. I know how these two kind of look similar, however, if you take a peek, the group attached to this carbon is different than the group that's attached to this carbon. So then we keep going. This one cannot be 1. This oxygen cannot be 1 because it has 2 sets of lone pairs on here. This has a double bond. This has 2 H's. This is a this is a chiral center, and so is this in nitrogen. So we should go up here. We cannot use this oxygen because it does not have 4 different things on it. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 chiral centers. We're supposed to draw the most stable conformer of cis 1,3-cyclohexanediol. In order to do that, we need to have an understanding of how to make chair configurations. We need to know that when the substituents are in axial positions, there tends to be more unfavorable interactions with axial atoms on the same side. These interactions are called 1,3 diaxial interactions, and this occurs between the substituents and they bump into each other. But then when the substituents are in the equatorial position, they are further away from each other, increasing the stability of the conformation. Therefore, the equatorial position is the most stable conformer of cis 1,3-cyclohexanediol. So first what we needed to do is draw the stepwise elimination mechanism using the arrow formalism of bonding, breaking, and bond making to predict the major product. What we need to recognize is this is an AE2 reaction. Everything is happening all at once. So what will happen is that the base of the sodium methoxide removes a proton from the beta carbon here, forming an ethanol. So we need to go ahead and draw that in here. So this oxygen will come down and grab this hydrogen. The electron pair in the beta carbon and hydrogen bond then forms the double bond here. And then the leaving group, which is the chlorine, will cleave off, draw my arrow there, cleave off with the electron pair and the carbon-chlorine bond, leaving us with a structure with this, with a now a new, there's our double bond, and it will give us the byproducts of ethanol and salt. And therefore, this is our major product. Question 7 is asking us to draw a stepwise mechanism showing the arrow formalism and show the product of the unimolecular substitution if the necrophile or solvent is methanol. So what we need to recognize is this is going to be a mixture of an SN1 and an E1 reaction. So what will happen is that the methanol will then, first it will cleave our lone pair here, the chlorine, will then cleave off, which is a slow mechanism, leaving our carbon cation right here. And then what will happen is that this oxygen will come around and grab onto our H, which then the hydrogen will leave behind the lone pair, and the lone pair will then make that double bond between the two carbons, the beta carbons, and we will end up with chlorine as a byproduct, CH3OH2 with a positive charge, and a double bond in our E1 reaction. Next, we need to draw an enantiomer of the given compound. So one thing that we need to remember is that an enantiomer is a mirror image, but it doesn't align. It is not superimposable upon each other. These are supposed to be considered chiral, but they do not contain a plane of symmetry. So one thing that I have done is we break this up here. That way, here's our mirror. This right here is our enantiomer. This is the mirror image that no matter which way you spin it, it will not be superimposable upon each other. And lastly, we will decide the IUPAC name for the structure given below. We need to follow the rules of IUPAC. We need to start with the lowest numbered carbon that has our substituent added to it. So I'm just going to start from the left going to the right and numbering our carbons. 1, 2, 3, 4, 5, 6, 7, and 8. So from there, my chlorine is on carbon number 3, so I wrote that down here. My ethyl group is off of my 6th carbon, so that gives us our 6th ethyl, and there are 8 carbons giving us the octane. Now, in order to decide if there is clarity on our group here, which there is because there is 4 different things attached to this carbon here. So to decide or prioritize it, we need to prioritize the atoms or groups of atoms attached to that chiral center here. So the higher the atomic number means the higher the priority. So because hydrogen is the lowest, this will get the 4, and more than likely you can kind of forget that. Chlorine has the higher atomic number out of the 4, so this will get the first priority. And R will go clockwise while S will go counterclockwise. So we will have a 1, 2, 3. So because of that, our clarity is S. It is counterclockwise. So this will give us the IUPAC name of S3-chloro-6-ethyl-octane. And this concludes my final exam. Thank you for watching.